perspectives of computer vision researchers on the challenges and opportunities for advancing visual interpretation technologies. Moderator, Daniela Massiceti, Senior Researcher, Microsoft. Speaker, Marcus Rohrbach, FAIR Research Scientist, Meta AI. Speaker, Andrew Howard, Senior Staff Software Engineer, Google Research. Speaker, James Coughlan, Senior Scientist, the Smith Kettlewell Eye Research Institute.
Hi, and welcome to the third panel discussion of the VizWiz workshop, everyone. My name is Daniela Massiceti, and I'm a machine learning researcher at Microsoft Research in Cambridge in the UK. And today I have the pleasure of welcoming three other fantastic computer vision and machine learning researchers to the stage. So we have Marcus Rohrbach, Andrew Howard, and James Coughlan. Now, I think we all know that there are no shortage of ways in which computer vision technologies can really support and empower the blind and low vision community. And so I'm really excited to have all three of you here today so that we can start to dig into the cutting edge research that's happening in this space. What are the key challenges that we're facing? And also looking forward, what does the future hold in this space? But before we dive in, I wanted to share a little bit more about each of you for our audience. So first, starting with Marcus. Marcus is a research scientist at Meta AI Research with a PhD from the Max Planck Institute of Informatics. Marcus is most well known for his work at the intersection of computer vision and natural language processing. And over his career, he has driven key progress in visual question answering, language grounding, and generating descriptions about images and videos, in particular movies. All of which are really highly relevant areas for the blind and low vision community. In fact, I myself have done a bit of work as well at this intersection of computer vision and NLP, and I think each of these fields alone have many open research challenges. And so when we kind of bring them together, we get even more complex questions that arise. So yeah, I'm really looking forward to what progress Marcus can share with us on this front. Our second guest is Andrew Howard. So Andrew is a senior staff software engineer at Google Research with a PhD in computer science from Columbia University. Andrew is most well known for his work in mobile-friendly deep learning models. So starting with MobileNet, then MobileNet v2, then MobileNet v3, and also MNAS-nets. His work really has been broadly adopted in deep learning packages like PyTorch and TensorFlow, as well as across a host of mobile phone platforms and apps. And I think many of us who work in computer vision research do have the intent of, deploying our models in the real world. And I think in many cases, a crucial part of that is obviously getting them to work on resource-constrained devices like mobile phones. So I'm really excited to hear more from Andrew on the latest and greatest in deep learning on the edge. And then finally, I'd like to welcome James. James Coughlan is a senior scientist at the Smith Kettlewell Eye Research Institute with a PhD in physics from Harvard University. James has been at Smith Kettlewell since 1998, and over this time has developed a really wide array of impactful technologies for the blind and low vision community. Some of these include guidance systems at traffic intersections, hazard detection for blind wheelchair users, wayfinding using machine-readable signage, interactive 3D maps, and object recognition tools. He has also driven fundamental research in computer vision, particularly graphical models and belief propagation for visual search and semantic segmentation. And I think as a person who really crosses, the spectrum from fundamental to applied research, I think James will be able to offer a lot of useful insights in the learnings he's made along the way. So yeah, welcome all. It's a pleasure to have you with us. And I think now that the introductions are out of the way, we can really dive into the panel. So to kick us off, and for the sake of the audience, I think it would be good if each of you could share a little bit more about your current line of work, how you got into it as a computer vision researcher, and a little bit about the problems that you're working on at the moment. So how's about we start with Marcus?
Hey, yeah, thank you for the introduction. Welcome, everyone. Yeah, I've been working basically on the intersection of vision and language since my master's thesis, and then continued working on different aspects of it. And most recently, we've been looking into, on the one hand, how to scale models so they can like multimodal models, so they can do multiple tasks, which I think is also useful in any applications, and learn from sort of unsupervised or self-supervised data. That allows to sort of increase the amount of data we can learn from significantly. That's sort of one line of research, and then another line which I sort of very recently just started this year is looking into the reliability of models. And with that specifically, I mean, if a model answers, for example, a question in a visual question answering system, sort of giving an answer, most systems right now just focus on predicting the most likely answer, but it might be not a good idea for some use cases, such as assisting a user or assisting especially a user with visual impairments, because the system might be wrong and the model doesn't really have a good idea when it's wrong and when it's right. So we have been looking into how good are models in predicting if they are right, and then they can answer the question, and predicting when they're wrong, or they can alternatively abstain, but just said, okay, I can't answer this question. I actually found, at least for state-of-the-art visual question answering models, that models are basically very bad at that. And we've been starting looking into how to improve that. And we have sort of initial work on that, but we're continuing working into how to really get that off the ground.
Yeah, that sounds fantastic. And yeah, when we think about, on your last topic of reliability, that's so important for people who are blind or low vision, because of the often safety critical scenarios in which, they may be asking a question about a visual scene in front of them. So yeah, I think those are really important directions. Thanks. Andrew, how about you? I know you're working very much on the edge, as they like to call it. So yeah, excited to hear a bit more about that.
Yeah, great. Thanks for the introduction and also the invite to speak. I think this is a great topic. Well, let's start from the beginning. How did I get involved in machine learning? I took some classes in undergraduate, and it was very clear that was the exciting place to be. This is, so then I did my PhD at Columbia in machine learning, and this was kind of before deep nets were a big thing. Then as I got in industry and kind of deep nets started to show themselves, it was kind of really clear, like, hey, we gotta, go tackle this problem here. Deep nets are the future. So I kind of independently worked for a little bit and did well in, say, the ImageNet challenges with maybe an eye towards a startup. But then a nice opportunity at Google came, and so then I joined Google. And they had a very exciting problem. How do we do this efficiently, on device? And so that was kind of how MobileNet was born. And basically, my team at Google is a kind of an applied research team where I would say 50% of our work is more about how do we move the field forward on the research side, but it's always targeted at, how do we solve a problem that's kind of useful for Google products and the industry in general. So kind of 50-50 between doing actual work that will go into the world and academic work. And then the two kind of inform each other. So one of the kind of challenges that's happened is, in the beginning, everyone kind of had a CPU on mobile devices, and, we could solve that well on there. And it's kind of a combination of how do we start from first principles, neural nets, how do we strip them down to the bare minimum and kind of make sure they map well to both the hardware and software available, usually targeting Android ecosystem. We're a little more focused on that. Now, as phones have gotten more mature, there's more and more kind of custom hardware. So some of the things that work well on CPU don't necessarily map well to running well on, say, accelerators. So one of the themes we've been investigating recently is how do we make kind of more universal models, models that out of the box are just going to kind of work well on any hardware you want to deploy them. Again, focusing more kind of on the Android ecosystem. And that's a combination of research topics around, again, what are the useful and efficient building blocks for a neural net, but then also a more applied aspect of, do the benchmarking, tune the model specific to the benchmarks on the hardware. And then what's kind of nice is, we get to publish that, we get to release open source models, but then we can also feed it in, say, Google products and kind of help a large number of people in the world. So that's kind of one theme, these universal models of efficiency that we're working on. I guess we have some other projects around how might we do more of a conditional computation, since not every vision task is as challenging. So simple things can be solved with less computation, more complicated things with more, and possibly more specialized. So that's kind of another theme. But yeah, in general, my work's basically around efficiency. How do we get kind of the highest accuracy for the least amount of cost?
Nice. Yeah, that's a great overview. And I think, if we kind of think about, I guess, the great diversity of devices, the heterogeneity of all the different devices that we use in our daily lives, having kind of universal ways of making, AI models on them work more efficiently is a really important direction, I think, going forwards. Thanks very much for sharing. James, love to hear from you.
Thanks a lot. And yeah, thanks also for inviting me to this panel. It's a lot of fun. I'll say a little bit about my background. I was sort of squarely in computer vision, doing my PhD thesis on things like deformable templates, stuff that preceded the deep learning, machine learning revolution. I always with an interest in geometry, and in my postdoc, I did this Manhattan World work. And back then, the interest was mostly theoretical. My advisor was thinking about possible applications for blindness. I think he was envisioning, a blind person navigating in an urban environment. A lot of urban environments have XYZ dominant structures. How might we interpret the edges? And that's how my answer to him was the Bayes net behind Manhattan World. And over time, I realized that the whole world of accessibility for people with visual impairments was just a great application for computer vision. And early on, I sort of faced a choice between, do I want to target people who identify as blind or people who are low vision? And the dividing line is largely what kind of interface do people want. If you are blind, you're going to want audio or tactile interfaces. If you're low vision, you're going to want something zoomed in, enhanced video, that kind of thing. And I thought, well, low vision people already have a number of tools at their disposal, but if I could do anything even small with computer vision, I could perhaps give information to a blind person that they would have no other means of obtaining. So I sort of focused mostly on blindness. And a lot of the themes over the years have been sort of geometric things that, where some sort of geometry is required. Like an early project was on navigation at traffic intersections and understanding where a person is with respect to crosswalk stripes on the ground. So for, just to say, my career has kind of gone from the theoretical side to more applied angles. And by the time I was doing, a Bayesian barcode reader, of course, I've always loved Bayesian reasoning, and this was probably begun in 2008 or so. But I was also very aware that at that time, there was no way for a blind person to, let's say, distinguish between two cans on their shelf. One could be tomato soup, the other could be, lentil soup, very different products. How do we read a barcode, noisy images, all that kind of thing? And I began, in those days, the N95 was just powerful enough that you could actually port some algorithms to it, and began doing user studies and realizing that the real work is to identify the overlap between, what does a blind person need and, where might methods from computer vision actually be practical in helping to meet that need. And it's always a big challenge to find that overlap. And so more recently, I've been focusing on two main projects. One is indoor navigation, or really, navigating in any GPS-denied environment. And trying to focus on a lightweight approach that, is relying on a small amount of information. So perhaps the best way to solve that problem, if you just want good localization performance, would be something where you scan, the entire environment and you make a 3D model and do localization based on that. But something which is more lightweight, that is more likely to scale and doesn't require connectivity, perhaps with sensitivity to privacy. Perhaps there's a building that you want to have access to, but maybe the manager doesn't want you scanning every portion of the building, but they can hand you a two-dimensional floor plan. So that's one of the projects I'm working on right now. And a big theme running through all of this, which is maybe a little bit, related to this whole panel, is that an image taken by a blind person is very often not going to be the image that you as a computer vision person hopes it would be. Aiming a camera is a huge theme in my work. And so, as a researcher making an application intended for a blind person, I don't want to assume a blind person can know where to aim. So I'm giving sort of generic feedback like, hold the camera forward, don't tilt it down, don't tilt it up, try to acquire usable images in that fashion. And another project that I'm working on is what we call Cameo, camera input output. And this was a project suggested to me some years ago by a blind person who said, James, can't you use computer vision to give feedback on, let's say, a three-dimensional object like a three-dimensional scale map? Or two-dimensional tactile map. And the idea being that you really want to sort of close the loop. A person who doesn't have a lot of vision is going to feel comfortable exploring something tactilely, but wouldn't it be great to have audio labels to orient the person to, you're touching a relief map. Well, this is, one mountain peak. This is another feature on the map. So that's another project I'm working on. And again, I'm thinking a lot about very practical issues like, this is currently in the form of an app, and the prospect of having a blind person aim a camera fairly precisely at a target object is kind of a challenge. And so these are important considerations that come up. And the general theme of these projects is just promoting accessibility whenever possible. And so while the first rung of the ladder is perhaps to have someone else, annotate an object so that it's then accessible to a blind person, the next rung above that is to make an authoring system that is completely accessible. So a blind person can author it themselves if they want. So that's an overview of where I came from and what I'm doing. So thank you.
Yeah, fantastic. You brought up a lot of interesting questions and a lot of interesting areas, I think, in particular for accessible tech. I mean, just going to one of the points you made around helping a person who is blind aim a camera. I mean, I think the kinds of images that we see in the real world taken by people who are blind are really quite different from the images we see in these computer vision benchmark data sets. And a big challenge there is, I think, making sure that we recognize that mismatch and are really building systems that work for the real world, not only on these benchmark data sets. Fantastic. So that was, I think, a very nice starting point for our discussion. Next, I'd like to hear from each of our speakers a little bit in more technical detail around the kinds of methods that they're using to tackle these problems that they've mentioned, or these areas, and in particular, the kinds of errors or limitations that you encounter with the methods that you use. So perhaps we can start. We'll shuffle the order a little bit. So perhaps we can start with Andrew. If we kind of look at these mobile deep learning networks, how do they work? What kind of makes them so mobile friendly? In what scenarios are they failing? It would be great to hear a little bit more. Our audience, I think, would enjoy to hear a little bit more about that.
Yeah, all right. That's definitely an interesting question for this area. In some ways, neural nets, basically, there's a trade-off between accuracy and resource usage. And, that could be resource usage, which is, latency or power, could be size. Generally there's a log linear relationship between these things. And whenever you're able to kind of find an improvement that is, more efficient, you can also find a more accurate one. So you basically have a curve, the Pareto optimal curve. And as you make an advance, the Pareto optimal curve kind of moves out further. So how does one move the Pareto optimal curve out? Some of it is, go into kind of first principles on how one might design an efficient network. And so how did we get to kind of mobile nets? It kind of came from the insight that, aspects of this were in the literature as I was developing it, that you could factorize networks into something responsible for essentially mixing the pixels and something responsible for mixing the channels. Hopefully not being too technical here, but and by doing that, you actually get a lot of improvement at speed. And one of the nice aspects is the part that mixes the pixels are essentially one-by-one convolutions, which are implemented as matrix multiplies. Now, matrix multiplies have been hyper-optimized in every format out there. That's like well understood, well worked on. So it's kind of moved most of the computation from a convolutional operator into a matrix multiply, which is simpler to implement. In fact, transformers, which are very popular for NLP and now for vision, they use a lot of these things as well, one-by-one multiplications. So we got essentially a nice advance by factorizing less total flops and then flops that map better to the hardware and the software. So that was kind of a nice win. And, those are the pieces that are typically getting used pretty broadly now. The small caveat is we still had to mix the pixels, and that's where we call these kind of depth separable filters. And that was kind of the challenge to make sure there was a good implementation of that broadly across the ecosystem, because that was a more kind of unique operator. So this goes more over to the general problem that we're having as we're trying to make advances in efficiency. So how do we measure advances in efficiency? So again, we could measure, are we more accurate at the same number of flops? But sometimes those flops won't actually map well to an implementation of the hardware and the software. Mm-hmm. So that may be interesting for academia, but for actually, shipping something and making an impact on the world today, it may not be the right solution. Might be the right solution in the future when you get good support. So this kind of iterative process of thinking about what are the pieces that will give kind of the best neural nets in the most stripped down version that then also map to the hardware and the software is kind of how we dig in. And so what are the tools that we use? Some of it is just first principles and thought experiments, followed by iteratively running experiments to verify that. Some of that is actual benchmarking. Some of that is then also using AutoML to kind of tune the pieces that we find to be useful in their kind of optimal shape. So this is kind of the research project as we try to create kind of best practices to do efficient networks. When I then engage with, say, a product team or something more applied, usually that's a little more linear. It's like, here's how well we can do now based on your requirements for the project, and, kind of follow the best practices on how to do that. But then if there's some gap between what, say, a product needs and kind of what we're able to deliver, that's another research opportunity, And so being able to take kind of potential product needs and map it back into the research community and then kind of do it as a more general research project, put it out in the literature and hopefully inspire more people to look at those projects. That's been a kind of a really nice cycle. So maybe I can pause there.
Yeah, nice. And I think that that really is the, what would you call it? Not the perk, but the real nice aspect, I think, of working in this kind of on the spectrum of fundamental to applied research, because you do get that nice loop where you're doing research, not for just the pure sake of research, but actually informed by kind of the real world needs, all the things that product teams want. So that's, I think, really a nice aspect. And I think James touched on that as well. Great insights into the mobile nets. I guess just a question from my own curiosity, as we see these mobile phone cameras, higher and higher res, they have these enormous images coming through now. Do you think the mobile nets are able to kind of make the most of those large images, or are we still in the space where we're kind of mapping these down to, smaller images, which will then work better and faster? So yeah, I don't know, is there a trade-off or a tipping point where, image size, what's the image size that current most efficient models work with on a mobile phone?
All right, that's a very interesting question. All right, so in general, I would say it's problem specific as to kind of what is the sweet spot for resolution versus accuracy. So, we use kind of, say, ImageNet or, COCO as kind of our lab rat, if you will, but that doesn't 100% map to real world problems. It correlates, and making progress there does tend to translate. But the idea of resolution for, say, an ImageNet problem, resolution's less useful there. However, things in computational photography, or things maybe if you want to do background blurring for one of these meetings, you got to have your edges really kind of clean. And so then higher resolution really benefits there. So these kind of mobile models, and they can be really scaled up as much compute as you have. So it's in some ways it's compute bound. And so as we get more and more accelerators, you can run on higher resolution, but then the gotcha is the accelerators are now a little bit memory bound, and then more pixels mean more memory. So some of it is like, when will the hardware be where you need it? But then what value do the extra pixels bring are kind of dependent on the actual problem.
Yeah, that definitely makes sense. I can totally imagine that different applications have kind of different resolution needs, let's say, or as you say, what is the value add that comes from those extra pixels relative to how much compute you're spending to process them? Great. Marcus, so you're working very much at this multimodal intersection, and there's been a lot of recent progress in this space with, I think, models like CLIP and DALL-E. And so, I'd love to hear a little bit more about the kinds of models that you're using at this intersection. How do they combine vision and language, and where are they failing? What are the kinds of things they're not working for just yet?
Yeah, so we are working also on very similar technology, like using transformers, as also mentioned by Andrew. And one thing we have been trying to solve is not just solving one single problem with a single model, but trying to have multiple problems which a single model can solve. So vision-only problems, language-only problems, and multi-model problems. And I think the challenge is especially to transfer it to tasks which are especially small with respect to the data. So, for example, if you think about the VizWiz data set, which this workshop is also hosting, it is comparatively small. So it's actually a challenge to transfer any models on this kind of task for assisting visually impaired users. So I think this is sort of a major challenge to understand how can we transfer from a large supervised training data or even larger unsupervised data. How can we transfer knowledge and data, given that the questions are different, images are different. So both the language and the visual side are basically changing, and we have to then also sort of understand how the model has to change. And that, similarly to what I mentioned earlier, then also the question is, if models operate maybe somewhat reliable on a large known set, how do they operate on this sort of new smaller set, and how can we solve that problem? And in our research, it's a largely unsolved problem, so there's lots of work ahead. And that will be also critical, I think, before one can sort of widely apply that and give that to users, basically.
Yeah, I think that's exactly right. And I think the point you're making around, I think it touches on what James was saying around really, this difference between perhaps this large supervised data set that we have, and really thinking about the ways in which that data may differ from the kinds of real world data that a person who is blind will collect, for which we might only have a very small subset. And so I think that is a very relevant challenge that we face in getting computer vision research models kind of working in that real world because of that mismatch. So I think that links nicely with what James mentioned earlier. James, I would love to hear a little bit more about the kinds of methods that have gone into the tech that you've built recently, and sort of what the limitations or errors you've encountered with these methods are.
Sure. Yeah, for the indoor navigation project, it's kind of a classical approach we're taking with, recognition of visual landmarks with YOLO, particle filtering, um, and something which I never appreciated. Maybe 5 years ago, I wasn't aware how powerful this was going to be. But visual inertial odometry, which of course is standard on any smartphone now. Which is a very useful input to have to your particle filter. And with that, we have a two-dimensional floor plan. So the components are, fairly well understood. There are a lot of challenges. Some of them are expected, some are unexpected. I mean, one of the expected challenges is that, recognizing visual landmarks, that sometimes you may have expectations about what kind of error rate you're going to get, but you may not attain that low an error rate right away. There's a challenge that's very pragmatic, but we're developing on iOS for our experiments, partly because a lot of blind people prefer iOS over Android. That's historical. It's changing slowly, because iOS, I think, was accessible very early on, even before Android. Android was accessible with screen readers and so forth. And developing on a smartphone platform, it's a bit of a hassle. I think of the computer as kind of the first world for programming. You have your all the programming tools you like. You can visualize things very nicely, 3D plots. You can mouse around, beautiful. But then when it comes time to port to the phone, it's difficult. So on the laptop or desktop, maybe you've had the luxury of using Python, and nothing against Swift, but Swift has to interface with C++, and suddenly you have a few different versions of the code lying around. And of course, you can visualize things on the fly on a phone, but that's the visual real estate is very small. So it's kind of a challenge, sort of iterating between these different forms of the code. And then just at a very high level, the very notion that, a blind person will use their camera on their smartphone to navigate. I mean, that's not a given. That's kind of an assumption that I made, knowing it was a questionable assumption. And what I found talking to some blind people say, I have no problem holding the phone while I'm walking. I'm always texting while I'm walking, or I'm always, using Google Maps while I'm walking. No big deal. For other people, though, it might be just, a reason they would never adopt such an approach, because maybe you have one hand already holding the guide dog harness or the cane or something. Maybe you have groceries in another hand. Oh, you want to hold this in another hand. That's maybe not going to work out. And so it's kind of made me more and more impatient to see wearable cameras become more widespread than they are, and in a way that would be perhaps integrated nicely with the user's phone. And then another sort of high level thing is, even if my algorithms are working perfectly, localization is working really well, that's great. There's a big question about how do you want to convey that information to a blind person. So I think a lot of experience that we've had in the field of accessibility over the years has been directed at sort of GPS enabled navigation, which is great. Typically, you're getting 10 meters accuracy, maybe 5 meters, even a little bit better nowadays in urban settings. But it's not pinpointing you. But in an indoor setting, you might actually want to tell the person, oh, you want to enter this door, not the door to its right. And even though they're separated by only a meter, they're very different destinations. So whereas before you could, in a GPS sort of domain, you could give broad instructions. How do you give more detailed instructions to a blind person? And, again, the system may know everything precisely geometrically speaking, but you don't want to burden the user with overly detailed instructions. And of course, this is often in audio form, and a person is going to have to listen for ambient sounds. That's a very important thing for safety. And, there are some conceptual tools that are very helpful. If you're in a corridor environment, it makes total sense to say, proceed down the corridor. And there's this technique that's used that's very common called shorelining. For instance, if you have a cane, you will sweep the cane back and forth while you're walking, and the cane will kind of help you keep track of, oh, the wall is right there on your left, and you're walking pretty straight. And then the next concept could be, oh, there's a junction, turn left at the junction. Okay, the cane can help you figure that out. But now if you're in an airport or some other wide open space, what directions do you give? You don't want to burden the user with, adjust your path by 2.5 degrees and, that kind of thing. So it's very unclear, I think, what the optimal user interface should be. And of course, different participants in your experiments will have different preferences, or circumstances may dictate that, hey, I don't need details this time, or yes, I do want all the details. So that's just some examples for one project. The other main project I'm doing on audio labeling. So the approach I'm taking for the time being, at least, is to do this as a three-dimensional thing. You have an object, like a tactile map or something, and the camera is estimating the pose of that, 6 degrees of pose, and then you have something like a stylus or or the person's fingertip, and you want to understand, well, where is the fingertip or stylus pointing in 3D, and how does that relate to the 3D object? So it's very basic geometry. But I want to think in terms of making software that works on as many cases as possible. And so I'm hoping for the day when pose estimation is just working really beautifully. But for instance, here's an object, a daily object. My mug has very few visual features, and I don't know if there are a lot of pose estimation algorithms that would run out of the box on something like that. And certainly, although, for instance, iOS has ARKit, which has a 3D scanning feature and will do pose estimates, it's looking for SIFT-like feature points, sort of older technology. So what I've done in the meantime is to say, well, let's go very low tech and let's use markers, Aruco markers, that kind of thing. And so, because I want sort of lowest common denominator, no matter how featureless your object is, I want to be able to sort of track the pose while I am simultaneously exploring, more advanced approaches. So anyway, that's a technical detail for that project. And in terms of sort of the user experience and what skills are needed, again, like my current approach is assuming that the camera has a clear view of the entire object of interest. It's not that easy, for a person who's blind to make that happen. And I also want to point out that even people with normal vision, we've all had the experience of maybe taking a selfie, and maybe the sun is blinding you. You can't see, the display of what the camera is showing you too well, and it's quite difficult, actually. So I think sighted people, we all know and pay lip service to the fact that aiming the camera is important and it's challenging. But I think we tend to forget the degree of our reliance on visual feedback to accomplish that aiming. So anyway, that's a sort of a technical challenge that comes up again and again on that project.
Yeah, thanks, James. I think there are a lot of connection points to some of the work from Andrew and Marcus. You mentioned, for example, visual inertial odometry. I think this is kind of, if we zoom out, it's really taking the perspective that, maybe building these systems, it's not just about the data stream that's coming from the camera, but really about how we can integrate all these other different modalities, whether it's natural language inputs or outputs, whether it's, the gyroscope or accelerometer, all of these additional pieces of information which might help us kind of help the model ultimately deliver a more robust and reliable output or response. So I think that's a nice connection point to some of Marcus's work. But then another point that you mentioned, I think, in one of your earlier answers, around, it's not just about us sitting in, as researchers, us sitting in our research worlds and, imagining what the experience should be. It really is about kind of mapping really testing them out, testing out those assumptions, making sure that they're, working for users, conducting user studies. You mentioned that in your one of your previous answers. So I think that's really important. It's not just about sort of keeping separate, keeping us as computer vision researchers separate from, the actual end users of this technology. It's about bringing us much closer to one another so that we make sure we're ultimately building technology that really serves the needs of the community. Great. So let's zoom out a little bit. And so I think, we've kind of got a nice base for, I think the audience will now have quite a nice basis or understanding of, kind of the work that you're doing, the challenges, technical challenges that you're facing. But I think given that you all, have worked in the computer vision research space for a long time, I think it would be interesting to kind of zoom out and hear a little bit more broadly about what you see as kind of the key turning points which the computer vision community has taken over the years or decades. Kind of those pivotal moments which have shifted the community in key ways and have really enabled us to address some of the challenges that end users or people who are blind face. Maybe we can start with Marcus.
Yeah, I mean, maybe I think there's maybe two things. On the one hand, the emergence of larger and larger data sets, especially in the vision and NLP community. But then second, obviously also especially in the multimodal setting, the start of deep learning, and especially for I guess it was for all the different machine learning communities, but also for the multimodal community, because it allowed to sort of really integrate visual and language signals, which was much more difficult before, because in vision, there was completely different technologies than in language. And so maybe most recently, that actually has come even closer with the emergence of transformers, where it's not just sort of the same system, it's actually the same model basically used for both vision and language signals. I think what we are now at is we are sort of really scaling to very, very large data sets and very, very large models. And there seems to be some gains to be made, but I think the next question is sort of how can we even do without those large data sets? So how can we do without these super large data sets and super large models and still perform very good? And I think there's sort of lots of advances to be made in the next coming years on sort of that side. And sort of the other side, I think we're sort of a big major challenge, I think, is in privacy and safety of the systems. And then I think that has, again, multiple dimensions. So it includes, for example, if you train on very large data, you don't really know what the system is trained with and how it might operate on certain points. You might not have seen it operate in certain dimension, but that might actually have seen this kind of object before in some far distance pre-training data and might suddenly be sure that it's something, but it's not. Or it is. So it's, I think there's lots of challenges to understand what those models can do and what they can't do, especially in the safety critical situations, if we want to deploy them for users which use them beyond playing with them.
Yeah, definitely. Some great points there. And I agree. It's kind of nice to see models like transformers really kind of bring together a lot of the work in, different parts of the community and almost serve as a universal model to rule them all. I think that's been quite a cool thing to see over the last year or so. James, how about you? What have been sort of the key over your career, the key turning points in the computer vision community?
Yeah, I mean, I think some of them are probably obvious, and I'll just say them really quickly. Computer vision algorithms used to be things that ran on desktops and laptops only, and the smartphone revolution has been really incredible. And of course, in the early days, we could eke some performance out of a Nokia N95, and then the iPhone came and all that. And I think some of the importance is, of course, it's amazing that you can run this on your phone. That's great. It's portable, it's mobile, but it's also been a real sea change in the way cameras are used. A camera used to be something that you maybe you kept charged for vacations or for special outings, whatever, wasn't always by your side. Now a camera is a daily tool. I remember very early on doing some of this research, just my mere presence, like holding a camera in a store or something. I mean, the store owner would question me, "What are you doing?" And there was, a note of concern. And fast forward to now, when I would think, especially if you're a blind person, you're holding your camera, you're scanning. I don't think people are going to suspect that you're up to no good. I mean, there's an assumption that this is a tool that's really useful. And so now you have cameras that are not special tools, but they're everyday tools. And so you have all this different data than you used to. And of course, the old training data used to be very nicely composed images. And now you have these images that are, that are much more informal, and a range of conditions limit their usability. So I think that's really great. Also, I think there's an increasing sort of tolerance of the fact that we're asking machines to solve tasks, and the tools we use, algorithms, AI, are imperfect, and that's not necessarily a bad thing. So I think there's an expectation that if you point seeing AI at something, usually works, but every so often it doesn't. It doesn't mean you throw it away. I think there's just more tolerance, especially maybe among the younger generation. This technology is growing. It's not perfect. And then just the other turning point, which is it's less big, but it's big for me, and I think it's big for a lot of researchers in accessibility, is the emergence of AR tools like ARKit and AR Core. ARKit came out in 2017. The amazing availability of visual inertial odometry, all this 3D geometry at your fingertips. It's really incredible. And I think a lot. Anyway, I'll stop there for now. I may have more to say about that, but I think that's been an incredible thing because it enables a sort of a spatial reasoning, 3D spatial reasoning that was really not there before.
Yeah, definitely. I think many of your points link quite nicely to Andrew and his work in kind of mobile-focused deep learning models. There's all this extra, all this extra stuff that comes with, integrating other information from a mobile phone. And we should have deep learning models that can work on these mobile phones in order to use all that info. So, Andrew, how about you? What have been in kind of deep learning on the edge, or I guess deep learning more generally, what have been the kind of key turning points you've seen over the last decade?
Yeah, let me maybe just work on deep learning in general to start. Both Marcus and James had some very nice answers, but I'll just very concretely say AlexNet. That was just the big turning point. It might sound obvious, but what was it? Right? It was proof of concept that feed-forward convolutional neural nets could work at high quality. And it brought together, again, the feed-forward convolutional net, larger scale data, and compute. And having those three kind of recipes together kind of set the stage for all of this. And I guess one other small neglected part is clever recipes on how to train it. Whether it's kind of, some of this is details, but these details are important. Whether it's kind of the distortions to kind of simulate large scale data, whether it's, small innovations like ReLU, like all these pieces all kind of came together in one package and said, hello world, deep nets are the way. And so going forward, the themes are around larger and larger models. So again, what we discussed, transformers showing their kind of universality, but they're very data hungry to have these kind of larger and larger, accuracies. Obviously, they're very compute hungry as well. So we haven't touched as much on the data side. Data is kind of the lifeblood of all this stuff. So I think some of the new results on, self-supervised and semi-supervised is very important. I think federated learning is very important. That's a way to kind of keep data private while still training joint models. And then, we touched a little bit on it's important what the models are being trained on, in that, you want fairness. And so maybe one thing to really, really anchor on here is test data is super important. How do you know you're doing a good job unless you have a really representative test set? Mm-hmm. And so, the VizWiz challenge is maybe one example of, you have data that's representative of the task you want to solve. Because while academic benchmarks are nice, when we actually want to deploy these things for real at scale, and so that they work for everyone, we need that North Star of evaluation data to make sure that things work for real, and then the fairness part, that they work for everyone.
Yeah, I think there's a great point, and I definitely agree on the AlexNet point. It really was the just the sort of coming together of so many things that then have really spurred on or initiated, catalyzed kind of the last decade of research in computer vision. But yeah, some other great points as well. All right, so we're almost nearing the end of the panel, and I thought to end off, it would be good to just get from each of you sort of 2 sentences or 2 points around, what does the next decade look like? What are the things that are going to be, what is the next frontier? What is the next big thing? Just kind of 2, high level 2 points around, or 2 sentences around what do you think is going to be the next big thing? So yeah, how's about we start with you, James?
Yeah, well, I mean, one thing that may not be on people's radar is augmented reality as something that's especially useful for blind people. And it can be done largely in the audio domain. We don't need to wait for affordable, comfortable headsets.
Excellent. Yeah, I think there's been a lot of growing momentum around AR, VR, and a lot of exciting links there to how it can improve accessible technology. Great point. Andrew?
Yeah, I think there's something around basically the ubiquity of all of these things. The tasks that deep learning can solve are becoming just a component that you can plug in, similar to the AR kit, AR core that you mentioned. And then what's on the kind of cutting edge is what are the new capabilities we kind of bring online as we scale the size of these large language models, these large vision models, the multimodal models that Marcus is working on, and others. So basically, what will those new capabilities be as things get very, very big?
Mm-hmm. Yeah, nice. Agreed. And wrapping up with Marcus, what do you think is the next frontier, the next big thing?
I would say probably the sort of the general assistant, sort of both sort of assisting visually impaired users, but also assisting all other users. I think there will be, right now, at least my personal experience, they're still a bit awkward to use most of the assistants. They have lots of flaws. But I think we will probably get in maybe the next 10 years to a stage where they're so good that they become more and more like the smartphone. Like maybe before a smartphone was there, nobody was saying, I mean, at least I personally wasn't thinking, how could that be useful? I think we might get to a stage in 10 years where like an assistant, a visual assistant for visually impaired users, or a general assistant for everyone, might be so omnipresent eventually that we might not know how to live without it. Similar how we don't know how to live without a smartphone, or lots of us don't.
Yeah, great point. And I guess, that directly links to your work at this intersection, because of course an assistant like that will need to have, the ability to both visually reason, but also lingually reason. So a nice, obvious place for your research, your current research. Great. Well, thank you all very much. We've sadly come up on time, so we'll have to wrap up our discussion here. But it's been really fantastic to have you all here today to learn more about the work that each of you are doing, and also to hear your perspectives on, how far computer vision research has come over the last decade or so, and also still how far it has to go. I hope that you've enjoyed participating in this discussion. Thanks again for joining us, and we'll say goodbye there. Thank you very much.
Thank you very much.
Thank you, Daniela, for organizing.
Thank you.